Hi and welcome everyone and Happy New Year. And we're very pleased to have Dr. Michel Thiebaut, the Schotten, as our speaker today. Michel is a director of research at CNRS at Bordeaux, head of the department of neurofunctional imaging in Bordeaux, and previously ran the brain connectivity behavior lab in Paris at Sorbonne, where he still holds a joint appointment, but he now moved it to Bordeaux. He's the editor-in-chief of Brain Structure and Function. He's the winner, and he's won several awards throughout his career. The ERC Consolidator Grant, the prestigious British Neuropsychological Society's Early Career Award, the Elizabeth Warrington Prize, as well as the European Society for Neuropsychology Cortex Prize. And he's also the incoming chair of OHBM. Congratulations. So his seminal paper in Science showed the first demonstration in humans that hemispatial neglect, which is this lack of awareness of items, things on one side in this visual field of view, could be reversibly produced by disconnecting the white matter. And this idea is being used worldwide in post-surgical assessments to prevent spatial attention deficits after surgery. But perhaps most of you know he's most famous for mapping the white matter anatomy in the healthy human living brain. And this was published as a series of important papers in the field with Marco Catani, and which finally led to his book, the Atlas of Human Brain Connections, which actually I have it on my desk here. And for those of you who haven't read it, it's really good, it's beautiful pictures, illustrations, visualizations, very nice explanations that actually ties the anatomy to circuits and function. And I really strongly recommend everyone who's working in BTI. So his latest work is exploring the role of white matter connections in the definition of functional areas, and which has led to the recently developed Atlas or the function of white matter. And he has an accompanying software that maps the influence of white matter circuits on function. He's also the developer of the BCB toolkit software suite, which is actually related to the talk today. So this is the first talk of 2022 with a radical title, the Disconnectome. And Michel is going to tell us what it is and how to compute it. So let's welcome Michel.
Thank you very much. Very nice introduction. It always feels the pressure, like when I have an introduction like that, I gotta perform after all this. All right, so let's jump into it, the Disconnectome. I'll start by saying, sometimes we're doing research and we kind of lose our way into like what are we actually doing. Like technically we're explorers, we're going into an uncharted field, collecting data and putting it together to try to build a story or understand the relationship between the different elements of those data. Unlike this illustration, that's Dr. Alice Roberts, was a researcher in evolution, and that in this beautiful picture, she showed like skulls that she collected on site, and she put it next to each other to demonstrate the evolution of the human brain. But we're not going to talk about brain evolution today. We're mostly going to talk about brain lesions, and particularly stroke lesions. As you may know, stroke is actually quite frequent. It happens every 2 seconds in the world. And patients who have a stroke, usually the first question that they have is, how will I be in a year or so? And it's very difficult to answer these questions. And technically, very, very poor at predicting the cognitive recovery in stroke. And this leads to not an optimal follow-up with those patients, because we cannot personalize very well the way we take care of them. And then we have no very good plan for rehabilitation and repair, for the same reason that we don't really know whether they're going to spontaneously recover or not. But besides the interest for the patients, also studying stroke gives us the opportunity to establish a link between a brain area and a given function through the exploration of the symptoms. And you may know like those 3 famous cases, which are really pillar of the behavioral neurology. On the left panel, you have a Phineas gauge, who in the 19th century had these metal bars that went through his skull and damaged his frontal lobe, and radically changed his personality. So he became irreverent and aggressive, couldn't control anymore his pulsion. And through the exploration of the trajectory of the bar, people started associating the damage caused by the bar to the orbitofrontal cortex and the medial frontal cortex to personality characteristic or the control of behavior. And that's how those brain regions started being tagged as personality and control of emotion regions. Then in the middle, you have a famous French case. That's the case of Le Borgne. Unfortunately, I couldn't find a picture of a portrait of his face, but I have a beautiful picture of his brain that I took at the museum. And following up lesions that he had in the posterior part of the inferior frontal gyrus, Le Borgne was not able to speak anymore, and his nickname became Tintin because he could only say Tintin all the time. And that led the behavioral neurology to tag really a brain area over there that they call the Broca area as the essential key region to produce speech. On the right, you have the case of Henri Molaison, which is like one of the most famous cases for people studying memory. He was an epileptic patient, intractable epilepsy, so drugs couldn't really help him. And he met this surgeon who offered him a simple solution, which would be to remove the areas that cause the epilepsy in his brain. And this neurosurgeon was allowed to zealous and removed bilaterally all the medial part of the temporal lobe involving the hippocampus and the amygdala. When Henri Molaison woke up, he was fine. He was able to speak. He kept the same personality. He was able to walk, but unfortunately, he was not able anymore to build new recollection. He lost his ability for short-term memory or episodic memory. And this is the most famous case that led us to think that the hippocampus and neighboring regions are critical areas essential for the establishment of episodic memories. In the middle, at the bottom, you have the first mapping of those brain areas and their dedicated function. I can name some of them. Like in 1, you will have the Exner area, which is for writing. In 2, you have the Broca areas that we just talked about. 3, 4, and 5 will be sensory motor area from the bottom of the body on the top to the top of the body at the bottom. Then you have the area 6, which will be, if I remember well, the Dejerine area no, that would be the apraxia area. 7, there will be the Dejerine area for reading, and 8 will be the area for comprehension, Wernicke area. And so on and so forth, with the idea that they could map the entire brain with different functions. It's very phrenologist if you think about it. And, you know, I like to be controversial, and we saw like how bad we try to change a little bit things and not think about the brain as a mosaic of regions that are dedicated to specific functions, but rather as a network where function emerge from the interaction between brain regions. And to do that, I had to develop some tools to do it. So I spent years to study tractography and dissect white matter tracts with tractography or postmortem dissection to really adjust the parameters of tractography that I do the best to match postmortem dissections and axonal tracing. And so with that, I thought I could probably build a prior of how everything is connected with everything macroscopically. And the idea was to project patients, as you can see here on this slide, onto this prior of how everything is connected with everything to produce what we call a disconnectome map, which is a heat map indicating areas that are the most likely to be disconnected in the brain. And so then instead of doing statistics on the brain lesions themselves, you do statistics on the probability of disconnection in the brain. And you can do all that without a toolkit, which is a BCB toolkit that you can find at the link at the bottom right of this slide. So what does it say about the three famous cases we just talked about? How does it change the way we understand really the deficits? And is this disconnection hypothesis as good as the lesion area hypothesis for the localization of function in those cases? Well, for the case of Phineas gauge, essentially the bar which damage orbitofrontal cortex and the medial frontal cortex in the left hemisphere also came up on the dorsolateral frontal cortex. And through its trajectory, it's disconnected the uncinate fasciculus, the frontalis land, as well as two important frontal connections that will connect kind of this cascade of brain region in the frontal lobe, which we call frontal superior and frontal inferior longitudinal. Those connections, when they are disconnected in animal, particularly the uncinate tract in cat, when it's disconnected, leads those cats to become like very aggressive. So they kind of match what happened with Phineas gauge. But then also the disconnection of those connections within the frontal lobe and this cascade of regions that are connected together kind of remind us of the branching model from Etienne Coquelin and how these regions that speak together allow to have a better planning of action. Which, if you read carefully the description of the case of Phineas gauge, which is freely available online, you can read the original papers from John Arlo, who studied him. Phineas gauge was going outside in his boot, without his boots and in pajamas when it was raining, completely lacking to check the weather or anything. Besides other cases that we know, as his friend saying it was no longer gauge, or him not being able to estimate really the value of money. So there is like a planning deficit that could be explained by this frontal disconnection. In the case of Le Borgne, really, mostly the lesion of Le Borgne have been described looking at the surface, but if you look at the MRI scan of the brain of Le Borgne, you can see that the lesion extended into the perisylvian white matter. It's like obvious, very, very visible. It's been first described by Nina Dronkas. And then, when you apply the Disconnectome method, you can find that really the entire perisylvian white matter disconnected, mostly the arcuate fasciculus, which is the most famous tract associated with a language. There is also a disconnection of the frontalis land tract over there, which might have also aggravated the symptoms of Le Borgne. Unfortunately, at that time, neuropsychology was not too advanced, so we have a very poor depiction of all the associated symptoms in that patient. In the case of Henry Mollesen, really the lesion damaged bilaterally a very important network, which is the limbic system. It disconnected the uncinate again, but also the fornix, the entire commissure, and the cingulum bilaterally. And now those tracts are very well known because they're easy to study. They don't cross so much with other tracts. So in monkeys, for example, if you damage the uncinate fasciculus, they're not able anymore to establish new memories associated with emotions. So I don't know how your memory works, but mine, if I have an event that happened to me with a big emotion, I will tend to remember it better. If you take the fornix, sometimes a human patient tends to have a cyst, which is in the third colloid, that can be removed by a neurosurgeon. And unfortunately, sometimes the neurosurgeon disconnects the fornix during the surgery, and patient come out with very quite bad short memory deficits and episodic memory deficits. And if you take the cingulum, which is in blue, the cingulum connects the hippocampus with the retrospinal cortex and the entire cingulate cortex. Really, the hub in there will be the retrospinal cortex that is showing most of the amyloid plaque, most of the reduced cortical thickness, most of the hypometabolism in case of Alzheimer's disease, which is a famous disease associated with episodic memory impairment. So, you know, I told you like two stories, one from the location of the lesions, another one which is explaining that actually it might be the circuit that is important. And at least, you know, I want you to think that those two stories are as plausible as the others. You know, take a leap with me and just start to believe. So I started, you know, exploring more systematically different syndromes and different symptoms after stroke or surgical lesions, and really associating with white matter tracks. And more recently, I thought, you know, what would be really great, that would be to try to create a map of every possible brain disconnection that might happen after a stroke and start classifying patients according to their location on these maps. And this is a work that I applied for to get my grant, my ESC grant, and really it's still taking from the metaphor of the explorer, still Alice Roberts over here. If you have this map, you can start understanding better the organization of things and making link between not only pattern of brain lesions and symptoms, but also the functioning of the brain. So the idea was to collect a lot of patients with a brain lesion, which I have been able to do thanks to my collaboration with Parashkev Nightchef in London, who kindly gave me 1,333 stroke MRI and lesions that we delineated. And so you can see an example on the top left, and converted in stroke disconnections. And we wanted to start looking at this distribution of pattern of disconnections. We didn't want to go blindly, because we know that stroke technically always happen in the same place. So we always wanted to contrast in every step we do the distribution of strokes. So you can see in the top rank of Bs, this is a distribution of stroke lesions. We always wanted to compare it to what if stroke was randomly distributed in the brain, to try to avoid to draw conclusions that would be due to the distribution of stroke only. And so we created this synthetic lesion distribution, which are fake lesions. They're exactly paired with a real lesion in terms of size and hemisphere that is damaged, except that they are randomly distributed. And then we started building maps. Those maps are maps where you have at the bottom clustered together. Each point is a different patient. In red, those are like real patient. In blue, those are like fake lesions that are randomly distributed. And we plotted it into a two-dimensional space using an approach which is Disney. And recently we moved to UMAP, but the result is very similar. And as you can see, well, brain lesions themselves don't cluster as much as we would have expected. They still keep a high level of variability. So that means that like one stroke is not always exactly the same as another stroke. However, if you start looking at the brain disconnection due to the non-random distribution of the fibers with a not completely random distribution of the lesions, actually you start to see very neat cluster or pattern of brain disconnection that repeat themselves in the brain. And so we saw that's interesting. And if we have cluster like this, it should be possible to model this variability in brain disconnection, compress it into simpler components. And the next step for us was really to simplify all the variability of brain disconnections in components. So when you take what we call the stroke disconnectome, because we have every pattern of disconnection that might happen in the brain, because we have more than 1,000 stroke lesions, and you run a principal component analysis on the disconnectome maps, you can see that after 30, that will be on the top left, and that will be the bar chart, the red part. After like 30 components, you already have 90% of the variance explained. And if you go up to 46, you have 99.9% of the variance explained. So you can model your disconnection in 46 dimensions. On the other hand, if you take the synthetic disconnectome, which would be fake lesion, randomly distributed, you can see that with 30 lesions, you just reach 80%. And if you take like the stroke lesions, that will be in green. If you'll never reach 100%. I mean, with 30 components, you just above 60% of the variance explained. So that's not a really good model. So we thought okay, we have those components, but those components have a specific pattern of connection, which will be a pattern of disconnection. So just for fun, we started like correlating it with pattern of activations to given tasks that we derive from the Neurosynth website. So we hacked the Neurosynth website, we collected all the data, and starting after selecting the one that were related to real functions, because you have a lot of stuff in there, we started correlating it with our components and see what was coming up. And what we found is that each component actually technically correlate quite well with a given function from Neurosynth, and this even correcting for multiple comparisons. So we thought, oh, this is interesting and surprising, how pattern of brain disconnection will lead to principal components that seem to match so well with function we know. And we thought, where does this come from? One explanation might be that it comes from the fact that function emerge from the interaction from brain areas, and the systematic disconnection of those brain areas will lead to the dysfunction, which is a very valid explanation. But we wanted to test something that was a lot more buzzy, I would say, which was, we've been starting thinking about the function, the division of functions through the exploration of brain lesions, essentially, as neuroscientists and neurologists. We started thinking about episodic memory because we had patients that had dissociation between episodic and semantic memory. Otherwise, we would have never done the difference between the two. So we wanted to test whether it was just a connection, or if eventually the distribution of brain lesions actually bias the way we think about brain functions, therefore biasing the way we studied it with functional MRI. And fortunately, because we have this synthetic disconnectome, we can test that. And that will be the bottom left of the window here. This is a relationship between the component of the stroke lesion, of the synthetic stroke lesion in green, of the synthetic disconnectome in blue, and the stroke disconnectome in red. And what we can see is the stroke lesion do not really match a pattern of activation that we can see with fMRI. And that's because we usually see networks with fMRI. We don't see a single area dedicated to one function. But when we contrast the stroke disconnectome, real lesion disconnectome components relationship with function with the synthetic disconnectome, fake lesion randomly distributed relationship with lesions, we can see that the stroke disconnectome is actually slightly better in red than the synthetic disconnectome. And this tiny difference is actually the bias that we have in the way we've been thinking about how function exists in the brain, because they are not driven by the anatomy or the connection, they're just driven by the bias of the location of lesion in the brain. But this is all number and scatter plot. I thought, you guys like to see brains. So then we can project back those components onto brains and see a little bit what's going on. And so for the first component, which I gave you an example, I just do 4 because I cannot do 46, otherwise you'll be all terribly bored. This one was correlated very much with articulatory task in functional MRI. And when we look at what it is, really, we can clearly identify here the arcuate fasciculus on the top connecting the Broca area and the Wernicke area, as well as the pars triangularis with some U-shape connecting the insula. And of course, all those areas are essential, critical for language. So component number 6 was correlating a lot with a navigation tasks. That will be, if you come back over here, that will be the one on the top right here. You can see like the distribution of the point are showing this correlation. And you can see that the pattern of disconnection associated with this was essentially disconnecting V2 area, maybe a little bit of V1, with the retrospinal cortex and the hippocampus and the parahippocampus cortex, which are like critical really for the navigation and those spatial maps that have been given the Nobel Prize a few years ago. Then, if you go for component number 10, which is another example, here we had the front area field, and on surface it looked like a single area, but you can see if you explore the white matter component, you can see that you have projections from one hemisphere of the brain to the other hemisphere of the brain through the corpus callosum, and the two front area field are highly tightly connected, one being a single area and the other one being divided in two, which is a recent finding that Mike Glasser has been demonstrating in his multimodal parcellation published in Nature in 2016. Then you come to functions such as calculation. If you look at calculation, technically, it's a big blob of white matter, which is in the depths of the intraparietal sulcus. And that's interesting because about 10 years ago, there was this beautiful paper from Andreas Kleinschmidt, who demonstrated that the Gassman syndrome would include a calcula was actually a disconnection of multiple U-shaped fibers in the depth of the intraparietal sulcus. So it's interesting how you can re-explore the brain, but from this perspective, the connections and associated with function and symptoms. So that was a relationship between each single component. That was the example of 4 components with function, but the supplementary material of the paper is showing all the components and they all have their little story that we extensively develop in the supplementary material of our paper. But then we saw, maybe some functions emerge from the association of the activity of this component. So we started decoding systematically a pattern of activation, meta-analytic activation from the NeuroSynth website with the 46 components, and then condense all our maps together in the next slide that I'm going to show to you, because then we have 500 maps. So I'm not going to show you 500 maps. I'm going to show you the top of the iceberg of those maps, which is the highest contribution of function the highest contribution of component to function. And then you can project it back directly onto the white matter. This is an axial slice. Now you can see some of the feature over here within the left hemisphere, some important language-related terms such as verb, fluency, lexical decision, pseudo words, and verbs and actions that will be in the lower parietal, while in the right hemisphere, you have inhibiting, maintaining, encoding, and tone. And the core of the brain, where you have the phonics, you have the memory, but interestingly, on the lateral portion of the phonics, you'll have a lot of association and context-related, task-related functional memory activation projected onto the white matter here. This is the top of the iceberg, and you know, at this point you might think, well, you know, it's nice, but how significant is that, Michel? So we created those effect size maps that you can see at the bottom left here, where you can see, well, we had effect size map, but one reviewer asked us to change it for goodness of fit. It's the same thing, it's all derived from the R value. But like here, the R value is always above 0.5, which is a large effect size, and reach 0.8, especially for the arcuate fasciculus. Some areas are like not as good, which technically are mostly located in the pons and a little bit in tiny pixel inside the cerebellum. But another important map that we've been building is how many function can load into every tracks. And so we call that the versatility map, and that will be in the label C in this picture, where you can see that in the left hemisphere, the arcuate fasciculus can actually load onto up to 70 different terms, while in the right hemisphere, you know, we're happy if we reach 5. And this result actually indicates that there is a huge asymmetry in the way we know functionally the left hemisphere compared to the right hemisphere, which does reflect also the way we've been exploring functions. It's easier to really see and dissociate different domain of language-related deficit after a lesion in the left hemisphere, while actually non-language or motor function are still poorly known, will be more dominant in the right hemisphere. And this clearly demonstrates that we have some more work to do in the exploration of functions. All right, so let's get back to the metaphor of the map. So I showed you that we created this map of pattern of brain disconnections that now we have and make available for all. We have those components as well. But if we come back to the map, really, we thought like, you know, what would be great will be beyond the projection of functions based on the component and the projection of white matter, of function onto the white matter, would be to really use this map of the distribution of disconnection and start locating on this map territories such as the valley of visual neglect or the hill of aphasia. And this idea was really to use this projection onto a UMAP, because it's easier to project it onto UMAP, and then project new patient on this map to enrich the map with neuropsychological information. So it's really like what I showed to you. We have the map and we take like 100 patients with visual neglect, and they happen to all locate in this pattern of disconnection. So we know that this territory is a territory of risks for visual neglect. Then we take like this group of patients that have memory impairment, and we project it into the space. They all have the same pattern of disconnection that is over there. And so we know that if we have a pattern of disconnection like this, we have more risk to have a memory impairment. This was a dream and was made possible by my postdoc student, Leah Talozzi, who managed to create the framework in a useful way. So this is the stroke disconnectome again, embedded with a UMAP this time. And you can see example at the top of pattern of brain disconnection with different kind of lesions and the probability of disconnection of the cortical spinal tracts, the IFOF, and the arcuate fasciculus in different color codes. And like I said, what we started to do is using another data set, because the first data set that I showed to you was still based on the 1,333 patients. But we use another data set of 150 patients that was extensively studied with neuropsychological tests that was like provided by Maurizio Corbetta. And we started projecting this patient in this space and building the territories, as I said to you, using threshold of correlations to see which were the sensitive areas for given test deficits. And you have the example here for motor deficit. You can see that you have a disconnection of the premotor cortex, but also the Rolandi opercle and the superior temporal gyrus here, as well as the caudate. And this will be related to this bottom corner in the left of the UMAP space. And then for language, you don't have a single solution for the Boston row performance. You will have different clusters that contribute to the score. And this is interesting because by using this approach, instead of doing lesion overlapping or disconnection statistic and contrasting different regions, here you can actually explore complementary pattern of disconnections that might be related to the same deficit the way we study it. The same is going on for the visuospatial attention with a strong callosal disconnection, the disengagement of the Posner paradigm here. And then what we did exactly the same thing as we did for the previous paper, but instead of projecting functional activations, we did project the name of the test directly on the brain. That's what you can see at the top of this slide. And then we did the same effect size map. This time we persisted doing F-square because that's what we should do for multiple regressions. And you can see that we have a high level of correlations, of a high effect size for those multiple regression. And on the bottom right, you have the versatility map, which interestingly is giving the reverse pattern as a functional activation map, which would suggest that actually the tests that we have are not sensitive enough and always load in the right hemisphere wherever your lesion is, while they're more specific in the left hemisphere because we know it better and we've been studying better. Doing the science and making those nice pictures was exciting, but we really wanted to engage everybody into this adventure and give anybody the opportunity to try. So we've been working really hard to build a web app, which is like already available. So you can go on the website by using the link that is at the bottom left here. That's a web app where you technically upload your Disconnectome map, and then you press run, and this will calculate for you, predict for you the neuropsychological profile of your patient, your single patient, based on its disconnectome. So we kept aside like 20 patients from the dataset of Maurizio Corbetta to check the validity of our prediction, which were quite good. We have like a 20% margin of error in the prediction, which is pretty good. And so you can see here, you have in the top, in the left column, you have the predicted value. In the middle column, you have the measured values. And on the right column, you have the subtraction between the two. I'll finish with my conclusion in two parts. So we showed that the redundancy in brain disconnection after stroke show a striking correspondence with task-related fMRI activation patterns. Aha, interesting. How does anatomy relate so well to function? This correspondence is due to the influence of the organization of white matter connections on the functional segregation of the human brain. And I've been showing that, but other people have been showing that you can define functional areas based on the pattern of connection with other areas. So, brain connection and how an area communicate with other area actually define very well the functional signature of this area. Sorry. But more than that, really, it seems that the bias distribution of brain lesions has biased our taxonomy of brain function, because for hundreds of years, we've been studying function looking at brain lesions, and if brain lesions are biased and some area never get damaged, we will never think about what those areas would be doing functionally in the brain. That's all the secret of epistemology. But however, we use what we have. We just like mentioning it here. We just use the current state of the art in task fMRI and white matter connection, and we put it together, and we build the first atlas of the function of white matter based on, a limited white matter measure, which is derived from diffusion. Sorry, my son is in the back. And our limited knowledge of the function of the brain, but we need to move on and provide this atlas and also highlight its limitations. These functions that we localize in this atlas correspond to the joint contribution of the areas that are connected by this white matter. This is really important because the concept here is we're showing the interaction and the function emerge from the interaction or the integration between brain areas. And then the part that I find the most interesting is, while those areas may help predict patient symptoms, the bias that we report that really provoke questioning and a motivation for exploring further as a very definition of the brain function as we know it, and exploring eventually new functions that we didn't think about, or brain areas that were poorly explored. And this, especially in the right hemisphere, because we've seen this big asymmetry there. So I got a lot of conclusion part 2. So we've seen in the space that different profile of disconnection can lead to the same neuropsychological deficits. And yes, you can fail at a task of reading because you cannot see, because you cannot read, or because you cannot speak. And this is really important when you use only one test and you do your correlation to see that those different pattern of lesion can lead to this different pattern of functional deficit that can lead to the same score at a given test. So if we look at this framework, we can actually explain and predict neuropsychological score with 80% accuracy, which was recently criticized by a reviewer. So we said 20% error, and this is a margin of confidence that we have in the exact prediction of the score. Our novel predictive framework is available as an interactive web application, so you can use it, you can test it, you can criticize it, you can tell us it didn't work for your patient, you can ask us to add stuff in it, you can, contact us with your group of patient lesions or anything, and we'll be happy to learn and teach to the space where this should be located and add it onto the website. This is completely on an open science, open data framework. And that's what I said, the web application is openly accessible and an invitation for researchers to test that population. And I see that I did 45 minutes, so I thank you very much. I thank very much all my teams. They've been really helpful and fantastic people, and I'll be happy to take your questions. Thank you.
Thanks, Michel, for such a nice talk. Any questions?
I have a question. Hi, nice talk. The brain imaging and stroke literature many years ago made a big deal of a concept, the concept of diaschisis. You have a lesion in one area, hypometabolic activity in distant area. Do you think that if you add also metabolic or functional information, you get even a better predictor of symptoms? And since diaschisis is a more dynamic thing, changes over time, do you think you can actually track that over time too?
So diaschisis took like different definition according to time and authors. And originally from von Monaco, the diaschisis was a white matter disconnection, and then it's been related to the hypometabolism. That can be related to, you get like a disconnection of like all the blood that can pump on a brain area, or you can also have an hypometabolism because the area is disconnected. Having said that, really all the perfusion of the brain is important, and we didn't include it into our model. It'll be great to have it, but that will require to collect data in thousands of patients with arterial spin labeling. I don't have the money for that, but I'm looking forward to see the data, and then we can do the same framework of embedding and looking at areas, or trying to build not a 2-dimension, but a 3, 4, 5-dimension space, which will be very inconvenient to show, but might be the ultimate explanation of what is going on inside the brain. Then finally, the more variable you put inside your model, the more you explain. But we recently compared this predictive framework with like predictive frameworks that will be based just on the lesion size and age of the patient, and this is explaining more variance.
Okay, thanks.
So I had a quick question related to Marco's question. So Marco asked about time. What about spatial propagation of these disconnections? So spatially, have you thought about any second order effects that kind of relate to sub-anatomies or sub-regions that finally cause these disconnections? So going through multiple hops to actually get a disconnection.
So I'm not sure I get your question. Sorry.
So when mapping these disconnectomes, you are essentially mapping the first order effects.
Yeah.
The direct connection. So have you thought about second order effects?
I see.
And
then like the disconnect on areas that will have an effect on another.
So kind of a spatial gradient over these disconnections over the brain.
So that so we try to look at this, and I think the graal behind this will be managing to combine very smartly the disconnector map with the method of Michael Fox, which is a network lesion mapping, which use functional connectivity. So sometimes people ask me, what is really the difference between functional connectivity and structural connectivity? Well, structural connectivity, we look at direct connection between area A and area B, and we hide the white matter. Those are the cables. Functional connectivity, you look at areas that communicate together. You skip direct connection. You can have indirect connection. You have an entire network. And this is a correlation. And this, while structural connectivity is like a solid wire connecting areas, functional connectivity is based on what wire together connect together, but not necessarily directly. The problem with functional connectivity is you don't really see the white matter, and the white matter functional connectivity is not so anatomically accurate. So you still need the structural connectivity. And I think like the key really to have a full picture will be to have a framework that combines the two. We recently developed another software which is called the Functionectome that combine fMRI with connection based on the weighted average. That we started exploring in that direction. But it's to do it well and being anatomically logical, so that even an anatomist can come and be like, oh yes, that does make sense. Require time and caution. Or at least that's the way I see it. It's a very good question. That's a good point. So yeah, there is a commentary from Mark Lemon. Nina Dronk says, I have a patient like that. Had also a lovely video showing how the patient, in spite of being able to produce only tauntaun, was still quite able to communicate with prosody and gesture, which will be if you look at prosody, it will be more the right hemisphere. In principle, dominant in the right hemisphere. It's not only the right hemisphere, of course. And the work of Elliot Ross, who was actually one of the people who work with Norman Geschwin, he's been really studying the right frontoparietal network, ventral, and its relationship to prosody in patients. That's quite a neat work.
Yeah, that's famous work. Famous work in the stroke.
Mm-hmm. That is nice. All right, we get another question. Some previous research show neuroplasticity help recovery in stroke patients. How would neuroplasticity may affect the construction of brain functional maps? Well, it's a very good question as well. So white matter tracks don't regrow. If you cut it, it's not going to repair itself. But if you have a tiny lesion, or if you're fortunate enough to have your language distributed more in the two hemispheres, then the proportion of damage that you have onto your language network is less, and you're more likely to recover. And that's something that we sort of demonstrated with Stephanie Falcon in 2014, that the size of the arcuate fasciculus as a surrogate for the dominance of language in the left or the right hemisphere was associated with better recovery when it was big in the right hemisphere, showing that you were more likely to have language dominance or equivalence in the right hemisphere with the left hemisphere. So, the plasticity of the brain works at best when you're younger. Unfortunately, as we're getting older, we have less neuroplasticity. And then stroke usually doesn't happen in young people. It does happen in young people as they tend to recover quite well. If you take the best example will be unfortunate kids that have a stroke very early in life or a brain lesion early in life. I've always been fascinated by how quick they recover from their brain damage at this age, while older people will really have a real struggle to recover. So yeah, neuroplasticity works. It just use different paths and networks to support functions. And then the proportion of networks that will be damaged will have an impact on this, negative impact on this neuroplasticity. I hope this is clear. Well, okay, good. You're welcome, thank you.
Michel, when you map the tractography to the disconnectome, this kind of a scalar measure, right? Do you align tractography across subjects, or do you rely on?
Yeah, so in the old time, I was aligning the lesion to every single subject, and then recently we have this new. So we work with a lot of people. We have a friend of us that have this code, Damien Wasserman, which uses a code that we use, and now we directly stretch the tractography in the MNI space. So we have hundreds of tractography, very high resolution in the MNI space that are freely downloadable on our website. You can directly download our tractography, and I call it best tractography, but that's from our perspective, which is really for the last 15 years, all we've been doing was to tune our tractography to match postmortem dissections and axonal tracing, because we are anatomists, and this is the way we think we should do tractography, which is different from people that come from a different background, which are computational neuroscience, and things that actually we should extract the most data we can from the diffusion imaging to connect things. And those are like different way of thinking and exploring the brain. I have no objection to the way they do their work, as they don't have any objection to the way I do my work. Those are beliefs and school of thoughts, and there shouldn't be a fight there.
So that means all subjects are in the MNI space.
Yes.
Before mapping it to before creating the disconnectome, as you say.
Yes.
And so the MNI space registration is really in a volumetric registration, I guess, and you are deforming the tracts.
Yes. You can do surface registration, because the problem with surface registration is that it is superficial. I'm sorry to be funny about it, but then how do you do with the structures that are inside, all the wires and saying? It's not only about aligning the cortex, it's the brain is an entire thing, and so in order to align white matter together, I create volume of high resolution tract density map, and I have a template of that, and I match my subject on this, and that gives like those very well aligned white matter connections that can help us to accurately calculate the probability of disconnections. Mostly I use a human connectome project at 7 Tesla, because with this level of magnet, your tracks are actually getting inside the gray matter. So you have like a better depiction of what it is anatomically, and a better coverage. So there is less subjects, and the tip of the temporal lobe is not as good as on the 3T, but you have a resolution of 1 millimeter instead of 1.25, which means your voxel are twice smaller. And then the magnet really gives these extra signals that allow you to get inside the white matter. It's just great.
And any thoughts on
gray matter? Sorry.
So these maps look very smooth.
Yeah,
very smooth. Why is that, you think? So the problem.
You mean the disconnectome maps?
Yes.
Lesion are big. That's why they're very smooth.
Okay.
You have a lot of connections, and then you still have a high variability from one individual to another, which is so we try to quantify this. We have this smart way of calculating how much is due to the noise, how much is due to true differences, and actually a lot of the signal is due to true differences from one person to another. Like our faces are different, our brain are different.
Okay.
A lot of difference in there.
So then in non-lesion studies, let's say, and I know you're working on lesions right now.
Yeah, no problem.
But let's say non-lesion studies, psychiatry, for instance, how can one think about these things or applying these things?
All right. So it depends if you have, do you have like diffusion weighted imaging in your psychiatric patient, or you don't, but you still would like to look at connections?
Yes, so we still have, we have DWI imaging.
Well, so that, I've been doing my postdoc for 7 years at the Institute of Psychiatry, working with people doing tractography in psychiatric cases, and this is great because so the context is different there. Like you still have, I don't want to offend anybody here, you still have psychiatrists that think that psychiatry is a disease of the mind and is not related to the anatomy. And you have Hewlett Jackson, which was in the UK and always pushed toward like psychiatry is, should have live imprinted to the brain and the biology. And then people have been doing a lot of MRI studies with contrasted results, and then tractography came in. And we started doing dissection and found those beautiful differences. There is this molecular psychiatry paper in psychopaths, convicted psychopaths, showing decreased connectivity, structural connection in the anciate fasciculus that connects the orbitofrontal cortex with the amygdala. I found it fascinating. You know, there was this autistic patient that have increased connectivity, if I remember well, in the cingulate cortex, like increasing the way they always into their self-thoughts. This is, you know, just think about like the symptoms you want to look at, and then dissect the white matter connections in the brain, and then do your correlation with your tract-specific measurement and your behavior.
Yeah,
that's
I guess,
to do it.
So I guess my question was, where you don't observe lesions, you don't have large disruptions. Would you? How is the sensitivity of this method in subtle changes? Again, non-lesion data. That's
as you would say. So the disconnectome, because you don't have lesion in psychiatric, you know, you're not going to see it. I have another solution for this. But what we're looking with the disconnectome is a macrostructural disconnection. We're looking really at the cables that are interrupted or likely to be interrupted. When you look at psychiatry, you're looking at microstructural changes. You're going to look at fractional anisotropy or hindrance modulated orientational anisotropy, or whatever way you want to modulate, you model the way water diffuse inside your axons. So the voxels are big, but what you're measuring is micro movement of water molecules inside your axons. And if your axons are not densely packed, the same as healthy controls, or kind of have leaking a little bit due to a very subtle pathology, or are not as big a diameter just through a neurodevelopmental disorder, then the way water is going to diffuse inside it will be different, and it will be captured by diffusion-weighted imaging. And then you study the specific network of interest, and it's extremely sensitive. It's so sensitive that I published in 2011 a paper showing that the asymmetry in the way connections are in the frontal parietal network can predict effect in LC controls such as pseudo-neglect. It's how much you're going to deviate when you have to point to the center of an object or a line, or asymmetry in reaction time. And that's LC control. So that really capture inter-individual variability here. But those are, you know, the different measurements. If you don't have, another thing is also if you really want to have a fine measurement, you need to measure in the native space. As soon as you apply stretching and deformation to your brain, you kind of smooth out any kind of fine differences. And that's why with tractography, we benefited from this fine measurement with water molecules at the microstructure. But also because we couldn't really bring it into the MNI space, we were forced to do manual job of dissecting every tracks manually. And this paid off with those beautiful correlations. Yeah, now that's about it.
Okay.
So sensitive enough if you give it enough time. If you don't have the tractography of your data, you can use a functionectome. You use then you can use, it's a little bit like the disconnectome, but for continuous values. So you can use cortical thickness or voxel-based morphometry values and project it onto the white matter using this weighting average approach that we have.
Okay, makes sense. So any other questions? If not, let's thank Michel again. And thank you very much, Michel, for giving a talk.
Thank you very much. Thank you for the invitation, and I hope to see you all in OHBM.
Oh, yes, definitely. All right. So this is the end of the seminar. See you guys next time. Bye.
Bye.